The pricing method, vertex cover. We now turn to our second general technique for designing approximation algorithms, the pricing method. We will introduce this technique by considering a version of the vertex cover problem. As we saw in Chapter 8, vertex cover is in fact a special case of set cover, and so we will begin this section by considering the extent to which one can use reductions in the design of approximation algorithms. Following this, we will develop an algorithm with a better approximation guarantee than the general bound that we obtained for set cover in the previous section. The problem. Recall that a vertex cover in a graph G equals to V is a set S which is subset equals to V so that each edge has at least one end in S. In the version of the problem we consider here, each vertex I in V has a weight Wi which is greater than or equals to 0, with the weight of a set S of vertices denoted W of S, which is equals to the summations of Wi, summing for all I in S. We would like to find a vertex cover S for which W of S is minimal. When all weights are equal to 1, deciding if there is a vertex cover of weight at most k is the standard decision version of vertex cover. Approximations via reductions. Before we work on developing an algorithm, we pause to discuss an interesting issue that arises. Vertex cover is easily reducible to set cover, and we have just seen an approximation algorithm for set cover. What does this imply about approximability of vertex cover? A discussion of this question brings out some of the subtle ways in which approximation results interact with polynomial time reductions. First, consider the special case in which all weights are equal to 1. That is, we are looking for a vertex cover of minimum size. We will call this the unweighted case. Recall that we showed set cover to be NP-complete using a reduction from the decision version of unweighted vertex cover. That is, a vertex cover is polynomial time reducible to set cover. This reduction says, if we had a polynomial time algorithm that solves the set cover problem, then we could use this algorithm to solve the vertex cover problem in polynomial time. We now have a polynomial time algorithm for the set cover problem that approximates the solution. This implies that we can use it to formulate an approximation algorithm for vertex cover. 11.12. One can use a set cover approximation algorithm to give an H of D approximation algorithm for the weighted vertex cover problem, where D is the maxima degree of the graph. The proof is based on the reduction that showed the vertex cover is polynomial time reducible to set cover, which also extends to the weighted case. Consider an instance of the weighted vertex cover problem specified by a graph G equals to VE. We defined an instance of set cover as follows. The underlying set U is equal to E. For each node I, we define a set Si consisting of all edges incident to a node I and give this set weight Wi. Collections of sets that cover U now correspond precisely to vertex covers. Note that the maxima size of any Si is precisely the maxima degree D, right? So, hence, we can use the approximation algorithm for set cover to find a vertex cover whose weight is within a factor of H of D of minima. This H of D approximation is quite good when D is small, but it gets worse as D gets larger, approaching about that is logarithmic in the number of vertices. In the following, we will develop a stronger approximation algorithm that comes within a factor of 2 of optimal. Before turning to the two approximation algorithm, we make the following further observation. One has to be very careful when trying to use reductions for designing approximation algorithms. It worked in 11.12, but we made sure to go through an argument for why it worked. It is not the case that every polynomial time reduction leads to a comparable implication for approximation algorithms. Here is a cautionary example. We used the independent set to prove that the vertex cover problem is NP-complete. Specifically, we proved that the independent set is polynomial time reducible to vertex cover, which states that if we had a polynomial time algorithm that solves the vertex cover problem, then we could use this algorithm to solve the independent set problem in polynomial time. Can we use an approximation algorithm for the minima size vertex cover to design a comparably good approximation algorithm for the maxima size independent set? The answer is no. Recall that a set I of vertices is independent if and only if its complement S equals to V minus I is a vertex cover. Given a minima size vertex cover S star, we obtain a maxima size independent set by taking complement I star equals to V minus S star. Now suppose we use an approximation algorithm for the vertex cover problems to get an approximately minimal vertex cover S. The complement I equals to V minus S is indeed an independent set. There's no problem there. The trouble is when we try to determine our approximation factor for the independent set problem. I can be very far from optimal. Suppose, for example, that the optimal vertex cover S star and the optimal independent set I star both have the size V divided by 2. If we invoke a 2 approximation algorithm for the vertex cover problem, we may perfectly well get back the set S equals to V, but in this case our approximately maxima independent set I equals to V minus S has no elements. Designing the algorithm, the pricing method. Even though 11.12 gave us an approximation algorithm with a provable guarantee, we will be able to do better. Our approach forms a nice illustration of the pricing method for designing approximation algorithms. The pricing method to minimize cost. The pricing method, also known as the primordial method, is motivated by an economic perspective. For the case of the vertex cover problem, we will think of the weights on the nodes as costs, and we will think of each edge as having to pay for its share of the cost of the vertex cover we find. We have actually just seen an analysis of this sort in the greedy algorithm for set cover from section 11.3. It too can be thought of as an pricing algorithm. The greedy algorithm for set cover defined the value of CS, the cost the algorithm paid for covering element S. We can think of CS as the element S's share of the cost. Statement 11.9 shows that it is very natural to think of the values CS as cost shares, as the sum of the cost shares, the summation CS summing for all S in U, is the cost of the set cover C returned by the algorithm, the summations of WI summing for all SI in C. The key to proving that the algorithm is an H of D star approximation algorithm was a certain approximate fairness property for the cost shares. 11.10 shows that the elements in a set Sk are charged by at most an H of the size of Sk factor more than the cost of covering them by the set Sk. In this section, we will develop the pricing technique through another application, vertex cover. Again, we will think of the weight Wi of the vertex I as the cost for using I in the cover. We will think of each degree E as a separate agent who is willing to pay something to the node that covers it. The algorithm will not only find a vertex cover S, but also determine prices PE which is greater than or equals to 0 for each H little e in capital E, so that if each H little e in capital E pays the price PE, this will in total approximately cover the cost of S. These prices PE are the analogous of CS from the set cover algorithm. Thinking of the agencies as agents suggests some natural fairness rules for prices, analogous to the property proved by 11.10. First of all, selecting a vertex I covers all agencies incident to I, so it would be unfair to charge these incident agencies in total more than the cost of vertex I. We call prices P fair if for each vertex I, the agencies adjacent to I do not have to pay more than the cost of the vertex. That is, the summations of PE summing for all E, which is equals to IJ, is less than or equals to WI. Note that the property proved by 11.10 for set cover is an approximate fairness condition, while in the vertex cover algorithm we'll actually use the exact fairness defined here. A useful fact about fair prices is that they provide a lower bound on the cost of any solution. 11.13 for any vertex cover S star and any non-negative and fair prices PE, we will have the summations of PE summing for all little e in capital E, which is less than or equals to W of S star. Proof: consider a vertex cover S star. by the definition of fairness, we have the summations of PE summing for all HE, which have ends I and J, is if we summing for all those PE is less than equals to WI, for all nodes I in S star, the vertex cover, and adding these inequalities over all nodes in S star, we get the formula at the top of the screen. That is the summations of summing for all index I in S star in the outer summation with the inner summation summing for all HE equals to IJ, summing for all the term PE is less than equals to the summations of WI, summing for all I in S star, which is equals to W over S star. Now the expression on the left-hand side is a sum of terms, which each of which is some H price PE. Since S star is a vertex cover, each HE contributes at least one term PE to the left-hand side. It may contribute more than one copy of PE to this sum, since it may be covered from both ends by S star, but the prices are non-negative, and so the sum on the left-hand side is at least as large as the sum of all prices PE. So that is our second formula in the middle of the screen. Summations of PE summing for all little e in capital E is less than equals to the doubling summation, where the outer summation is summing for all index I in S star, and the inner summation is summing for all HE, which is equals to IJ, and we're summing the term PE. Combining this with the previous inequality, we get that the summations of PE summing for all little e in capital E is less than equals to W over S star, as desired. The algorithm. The goal of the approximation algorithm will be to find a vertex cover and to set prices at the same time. We can think of the algorithm as being greedy in how it sets the prices. It then uses these prices to drive the way it selects nodes for the vertex cover. We say that a node I is tight or paid for if the summations of PE summing for all E equals to IJ is equals to WI. Now the algorithm is as follows. Vertex cover approx of parameters G and W, where G is the graph and W is the weight. We set PE equals to 0 for all little e in capital E. So initially all the H has prices 0. Well, there is an H E equals to IJ such that neither I nor J is tight. We select such an HE and we increase PE without violating fairness. Then after we break out from the while loop, we let S be the set of all tight nodes. Then we return S. So for example, consider the execution of this algorithm on the instance in figure 11.8. Initially, no node is tight. The algorithm decides to select the H AB. It can raise the price paid by AB up to 3, at which point the node B becomes tight and it stops. The algorithm then selects the HAD. It can only raise this price up to 1, since at this point the node A becomes tight, due to the fact that the weight of A is 4, and it is already instanted to an H that is paying 3. Finally, the algorithm selects the HCD. It can raise the price paid by CD up to 2, at which point D becomes tight. We now have a situation where all edges have at least one tight end, so the algorithm terminates. The tight nodes are A, B, and D, so this is the resulting vertex cover. Note that this is not the minimal weight vertex cover that would be obtained by selecting A and C. Analyzing the algorithm. At first sight, one may have the sense that the vertex cover S is fully paid for by the prices. All nodes in S are tight, and hence the edges adjacent to the node I in S can pay for the cost of I. But the point is that an HE can be adjacent to more than one node in the vertex cover, i.e. if both ends of E are in the vertex cover, and hence E may have to pay for more than one node. This is the case, for example, with the edges AB and AD at the end of the execution in figure 11.8. However, notice that if we take edges for which both ends happened to show up in the vertex cover and we charge them their price twice, then we are exactly paying for the vertex cover. In the example, the cost of the vertex cover is the cost of nodes A, B, and D, which is 10. We can account for this cost exactly by charging AB and AD twice and CD once. Now it's true that this is unfair to some edges, but the amount of unfairness can be bounded. Each edge gets charged its price at most 2 times, once for each end. We now make this argument precise as follows. 11.14. The set S and prices P returned by the algorithm satisfy the inequality W of S is less than or equals to 2 times the summations of PE, summing for all little e in capital E. Proof. All nodes in S are tight, so we have the summations of PE, summing for all E equals to ij is equal to Wi for all I in S. Adding over all nodes in S, we get W of S is equals to the summations of Wi summing for all I in S, which is equals to the doubling summation summing for all index I in S, and with the inner summation summing for all E equals to ij, summing with the term PE. And HE equals to ij can be included in the sum on the right hand side at most twice if both I and j are in S. And so we get W of S is equals to the summations of I in S with the inner summation summing for all in I equals to ij summing for all PE, which is less than or equals to 2 times the summations of PE summing for all little e, which is in capital E, as claimed. Finally, this factor of 2 carries into an argument that yields the approximation guarantee. 11.15. The set S returned by the algorithm is a vertex cover, and its cost is at most twice the minimum cost of any vertex cover. Proof. First, note that S is indeed a vertex cover. Suppose by contradiction that S does not cover HE equals to ij. This implies that neither I nor j is tight, and this contradicts the fact that the while loop of the algorithm terminated. To get the claimed approximation bound, we simply put together statement 11.14 with 11.13. Let P be the prices set by the algorithm, and let S star be an optimal vertex cover. By 11.14, we have 2 times the summations of PE summing for all little e in capital E is greater than or equals to W of S. And by 11.13, we have the summations of PE summing for all little e in capital E is less than or equals to W of S star. In other words, the sum of the H prices is a lower bound on the weight of any vertex cover, and twice the sum of the H prices is an upper bound on the weight of our vertex cover. W of S is less than or equals to 2 times the summations of PE summing for all little e in capital E, which is less than or equals to 2 times W of S star. So we can say it's 2 approximation algorithm.